Section 2.5 then, we're talking about coding data. Now this is an odd topic in some ways, because in a lesson, your teacher will probably tell you, if you're in my class, I've probably told you, the point of coding is that we start with a bunch of numbers like these ones. So just take these ones out of example 10, and we think, oh, they're nasty numbers, they're difficult to deal with, they're numbers in the 300s. So I'll code them to make them easier numbers to deal with. So when I use this coding, then the coded numbers are here, and they're much nicer to deal with. They're much easier to deal with and do calculations with. Now, there's two reasons that that's silly. First of all, with this particular coding question, the coded data, the Y data, isn't a great deal nicer to deal with than the X data in the first place. And secondly, who cares how difficult the numbers are? If we understand the calculations, we can obviously program them into a graphic calculator or program them into a spreadsheet, and there's, it doesn't matter if they're difficult numbers to deal with. We don't have to do calculations by hand. So the real reason is because getting your head around this coding idea is useful later on. It's another one of those learn it, trust me, wait and see, and we'll use these ideas in other places. So bearing that in mind, we need to get used to coding data. And here's the idea, okay? If you imagine your set of data spread out all over the number line, then I take every single piece of data and I add 6. What's going to happen? Well, every one of these bits of data is going to move up the number line. So the way I always think about it is if my fingers are the bits of data on the number line, adding 6 is the equivalent of just doing this, just moving them all up the number line, just sliding every bit of data up the number line. So what happens to the measure of spread, and what happens to the measure of location, or the measure of average, right? Well, the average is going to go up by 6, isn't it? If all the pieces of data go up by 6, the average goes up by 6. The spread, though, doesn't change, does it? The way that these pieces of data are spread out and how far away they are from each other, or if you just think about the range hasn't changed. Nothing about the spread of the data has changed, but the average of the data is increased by 6, okay? What happens if let's start again, I've got a load of data on the number line here. If I times all that data by 6, then everything gets 6 times bigger, so they sort of move over here. Now, they are going to be 6 times more spread out, because that distance between the lowest and the highest has got 6 times more spread out. All the relationships between the bits of data and how far away from each other they are, all of those have been times by 6 as well. So the spread gets 6 times bigger. Also, the average has increased as well, and it's got 6 times bigger as well, hasn't it? And then you can run through the same sort of argument. If you take away 6, the average decreases, but the spread doesn't change. If you take a set of data and divide by 6, the spread changes and the average changes, okay? So the point of that is, if you have a bunch of data that we're going to call our X data, like these numbers here, and we change them by taking away something and dividing by something, then we're going to change our X data into our Y data. So here's the table, look, here's the X data on top, here's the Y data. Now we do the calculations with the Y data, and we can find the standard deviation of the Y data and the mean average of the Y data as well. So the Y bar is 3, and sigma Y, or the standard deviation of the Y data, is 1.72. Now what we'd like to know is, what was the average of the original data, and what was the standard deviation of the original data? Well, when I took away, with the coding, when I took away 300, that affected the average. When I divided by 10, that affected the average. So how did it affect the average? Well, when I took away 300, I took 300 off the average. When I divided by 10, I divided the average by 10. So if I go the other way around, I take the average of the Y bar and times by 10 and add 300, I get the average of the X data. In other words, I can solve this equation, and that gives me the average of the X data. Now with the with the standard deviation, with the measure of spread, when I took away 300 in coding the data, that didn't change the measure of spread. So sigma X divided by 10 gives us 1.72. When I divided by 10, that did change the measure of spread. So to get back to the original measure of spread, I have to times by 10. So in other words, we ignore the adding or taking away bit when we're dealing with the measure of spread, okay? Only other thing to point out is that the measure of spread is the standard deviation. If you're asking for variance, then you need to make sure that you've found the standard deviation and then square it afterwards, because the standard deviation is the measure of spread that we're using, as discussed when we were talking about the last section of this chapter. That takes us up to the end of chapter 2.